Okay, wonderful. Welcome everyone. Welcome to today's webinar, which is part of the Young Scholar webinar series on climate change, macroeconomics and finance, organized by the eAxis Forum. I'm Connor Walsh and I'm your moderator for today. I'd also like to welcome our PhD student committee who we've got with us. And in today's webinar, Adrien Bilal will explain his research with Diego Kanzig on exploiting natural variability in global temperature and using time series variation to estimate the macroeconomic damages from climate change. Adrien Bilal is an assistant professor of economics at Stanford University. He's a macroeconomist who works on topics related to climate change, spatial, and labor economics. Before joining Stanford, he was an assistant professor at Harvard University's Department of Economics, a postdoctoral fellow at the University of Chicago, and he earned his PhD from Princeton University. So we're very happy to have Adrien here. Just a reminder on how it works. Adrien will take some clarifying questions during the presentation, which will be around 45 minutes, but most of the substantive Q&A will leave for after his presentation. If you've got a question, please ask it in the chat and I will ask Adrien directly. And without further ado, Adrien, take it away.
Well, thanks a lot. Thanks a lot, Connor, for the invitation. It's a pleasure to be here. So I'll talk about the macro impact of climate change, global versus local temperature, which is joint work with Diego. All right, so the starting point of this paper is that you often hear climate change being described as an existential threat. You can hear that if you talk to some of your friends. You can hear that if you read the popular press. You can also hear that if you've been listening to what climate scientists have been saying for decades, saying that the scale of the transformations that climate change will bring about is going to profoundly affect our livelihoods and the economy. But if you turn to the economics literature and look at what people have estimated, you actually see a very different story. So there's a huge literature, and here I've only listed some of the very influential papers in that literature that have looked at the impact of temperature on economic activity, and they find pretty moderate numbers. So across this literature, we find numbers like 1, 2, or 3% of GDP per degree Celsius. Now, if you put that against background economic growth, 2% per year, and any plausible discounting, living in a 3-degree world by the end of the century doesn't sound that alarming. There's a catch, however, which is that all of these estimates rely on variation in temperature that is country specific, so that is local temperature. And so what we want to ask in this paper is twofold. First, is it the case that the consequences of climate change are moderate at most, or perhaps is it the case that local temperature provides an incomplete representation of the consequences of climate change? And so what we do in the paper is to first provide new macro estimates of the impact of temperature on economic activity. What we propose to do is to shift attention from local temperature to directly global mean temperature, which is the object we're interested in when we listen to what the IPCC says, and is also, we think, a better summary statistic of climate change. So that's going to pose some challenges, but fortunately, there's plenty of variation in global mean temperature directly that we can exploit natural climate variability. And so we're going to rely on that variation, which is going to be mostly time series variation. Our headline number is that a 1 degree Celsius increase in global mean temperature implies a 12% decline in world GDP at peak, which is 6 to 7 times larger than what you find if you look at local temperature. And in our case, we find 1.5% per degree Celsius, consistent with the conventional estimates in the literature. So, obviously, when you start seeing large numbers like that, you get a little nervous. And so we're going to go through a long list of exercises that hopefully will convince you that we're capturing the causal effect of global temperature on economic activity. Then the next question is, why is it the case that global temperature is so much more detrimental to economic activity than local temperature? And so what we show in the paper, after collecting a large and assembling a large data set on world extreme events, is that global temperature changes actually correlate much more strongly with damaging extreme events than local temperature changes. And so when we add up the economic impact of all of these extreme events mediated through the effect of global temperature, we actually get quite close to our 12% number. In the last part of the paper, we then use these reduced form estimates to then inform a very simple structural model to get at welfare and the social cost of carbon. So we're going to target our empirical estimates and back out structural damage functions in a very simple neoclassical growth model type of environment. And then there we can, run several experiments. The first one is to say, well, what happens when we emit 1 ton of carbon in that environment? So that's going to let us calculate the social cost of carbon. And when we target our local temperature estimates, so the conventional estimates, if you like, we find a social cost of carbon of around $200 per ton. So very much in line with what the EPA uses these days. If we target our global temperature numbers, however, we find something much larger, 4 to 5 times larger, in the vicinity of $1,000 per ton. Another way of looking at these numbers is to ask, what would happen if temperatures would rise gradually and reach 2 degrees C plus 2 degrees C by the end of the century, relative to today. Well, under the global temperature estimates, that implies a 29% present welfare loss. So that's about the same magnitude as the 1929 Great Depression, but experienced forever because climate change in this environment is permanent. So there's, however, one silver lining to these results, which I'll discuss more at the end, which is that when you reach a world with large social costs of carbon, even domestically for large economies, say like the US, the cost of carbon is still pretty large, even if they don't internalize what happens in the rest of the world. And so our numbers actually imply that decarbonization is unilaterally optimal for large economies like the United States. So let me not spend too much time on the literature review. I'll just simply say that our main, the meat of the paper is really to shift attention from local temperature to directly global mean temperature. Okay, so let's get into it. So the nature of our exercise is to try to estimate the causal effect of global temperature here in the left panel on world GDP on the right panel. Now, as you can see, temperature has been gradually trending up over the last 60 years. And this also doesn't come as a surprise. World GDP is also trending up over that time period. So of course, if we just regress GDP on temperature, we're going to get a positive number, and that's simply going to reflect the greenhouse effect. The economy grows, we emit more, these emissions warm the planet, and so we see temperature going. So we have to do something a little more involved. And so that's basically going to be to detrend this time series of temperature and then rely on these year-to-year fluctuations in global mean temperature that you can see here that are actually plausibly orthogonal to the slow-moving greenhouse effect. So there are many ways you can detrend the data, and we go through a number of ways in the paper. So here I'm going to show you the one that we lead with, which is the approach by Hamilton, which is to regress temperature on a bunch of its lags, and then we extract the residual from that regression, and that we're going to call a temperature shock. And so the fact that we regress on multiple lags of temperature takes out the trend and allows for some flexibility in that trend. And then the innovation is the temperature shock. Now, to specify exactly the details of this Hamilton filter, it's useful to think a little bit about the type of variation that drives temperature around the trend. So there are two types of sources. There are external causes, solar cycles, for instance. Every 10 years or so, the north and the south poles of the sun flip. That changes the amount of energy that's radiated by the sun, and so it changes temperature on Earth. Volcanic eruptions also tend to cool the atmosphere because of sulfur emissions. Then there are internal causes, such as the El Nino-La Nina cycle, which, because of the internal workings of the climate system, tend to move around global mean temperature as well. So a lot of these phenomena have some degree of internal persistence. They're not over after 1 year. And so we're going to choose a prediction or horizon in this regression of H is equal to 2, so that we make sure to capture somewhat persistent climatic phenomena in line with this intuition that I've just discussed. Now, you may say, well, why not H is equal to 1? Or, we also do that in the paper. Actually, we do all sorts of detrending approaches, and we always find the same numbers. Okay, so this is our series of temperature shocks after we apply this Hamilton filter. And so it's basically the previous line without the trend. So you can see that it's centered around 0, moves around over time. And also keep in mind that the typical size of these shocks is not 1 degree Celsius. It's smaller. It's 0.1 degrees Celsius. We never see a 1 degree Celsius shock in the data. And so we're going to rely on these moderate fluctuations for identification, just like in the local temperature approach. The literature also relies on moderate fluctuations in local temperature for identification. So once we have these temperature shocks at hand, we run a completely standard local projection, which is basically just a series of regressions at different horizons. So we project, GDP H periods in the future on the temperature shock at time t, and then we're interested in these coefficients theta h, which trace out the entire impulse response, so the impact of a temperature shock at time t on GDP at all possible horizons. And we also include a number of controls in this regression that I'll discuss a little bit more in a few slides. Okay, so before we go into the details of the controls and everything, let me just show you our main results, which is the effect of a 1 degree Celsius global temperature shock, so scaled up from linearly according to a linear specification on world GDP. Okay, so you get a 2% decline in world GDP on impact, and then this effect gradually worsens over time, and so 6 years out actually reaches a 12% decline in GDP, and then after that, the effect mean reverts. So that's a large peak effect, but it's also important to keep in mind that in the background, the level of temperature doesn't go back to zero immediately after a temperature shock. It stays elevated for a little while, and so this 12% number, 12% effect happening 6 years out actually reflects partly the accumulating effects of this persistently elevated temperature. And so in the estimation, we're going to take that into account, of course, so that we can correctly construct our counterfactual. All right, so of course, you see this number and you start worrying that maybe something is amiss. And so, of course, we also faced this type of skepticism towards this number initially. And so we went through a long list of exercises that I'm going to show you now that hopefully will convince you that this is actually the causal effect of temperature on world GDP. So the first concern is omitted variable bias. Perhaps it just so happens that it's very hot every time there's a recession, but the recession happens for reasons unrelated to temperature. And so that could bias our coefficients. Okay, so that would be omitted variable bias. Reverse causality is also a concern. Once GDP starts declining, emissions also fall. And so going forward, the world warms less than without this feedback between emissions and temperature. And so we want to account for that. Perhaps our estimates are not externally valid. Perhaps they vary over time or by type of temperature shock. And then finally, you could have omitted variable bias at the regional level. And so we're going to deal with concerns 1 and 2 in this time series context. Then we'll move to the panel, and there we're going to deal with 3 and 4. And then in this panel setting, we'll then be also able to contrast our global temperature estimate to the more conventional local temperature estimate. Okay, so concern number 1, omitted variable bias. So in a time series context, of course, you don't have that many data points, and so you're worried that maybe you're picking up just some spuriously correlated shock. So in fact, in the baseline estimate that I've shown you so far, the black line here, we've already controlled pretty flexibly for the world economic cycle. So we include 2 lags of temperature, 2 lags of GDP, and importantly, dummy indicators for all of the major world recession periods, the oil shocks in the 70s, the financial crisis in 2008, and so on. Now, if you take out the world recession indicators, actually, if anything, that attenuates our main effects a little bit. That's the dashed red line, although not particularly strongly. And you can also expand the set of controls relative to baseline at global oil prices, the US T-bill rate, and then you get the yellow line, which basically lies on top of our baseline estimate. So it doesn't seem that our estimate is particularly sensitive to the set of world controls that capture the world economic cycle. So that's already telling us that omitted variable bias is unlikely to be a major source of concern here. Now, to visualize that very clearly, what we're showing in panel B is a scatter plot. Is basically all of the identifying variation that identifies the point at H is equal to 5 here. So we have the temperature shock on the x-axis and GDP per capita here on the y-axis, and then every year corresponds to 1 data point that we're using. And what the scatter plot shows is that our results don't seem to be particularly driven by any particular outlier, and so again, that's telling us that these results are unlikely to be driven by omitted variable bias. All right, so now we can move on to concern number 2, which is reverse causality. So the concern here is that, well, once GDP starts declining, CO2 emissions go down, and then that affects temperature going forward. But that affects temperature by making it less elevated than otherwise, and so that means that we're underestimating true damages because of this feedback from greenhouse gases back to temperature and GDP. Now, there are 2 reasons to think that that's not going to be a massive deal. The first one is these year-to-year fluctuations in emissions are fairly small compared to the accumulated carbon stock over the last 200 years. And so we shouldn't expect, a massive adjustment. And to make that argument precise, what we then do is in this, the second part of this argument is to actually explicitly adjust our estimates in a bivariate analysis by using, a simple climate model that connects the emissions back to temperature, which we can then connect back to GDP. And so these are the three lines that you're seeing here. The dashed red line is the one where we adjust for the feedback between carbon dioxide emissions and temperature. The yellow line is when we add methane into the mix. And the dotted purple line is when we add sulfur dioxide, which is an aerosol that actually works in the opposite direction as methane. So these are the three major contributors to changes in radiative forcing for the atmosphere. And you can see that none of them make any meaningful adjustment to our baseline estimates, again, for this intuitive reason that these year-to-year fluctuations are just not very big. Okay, so far, hopefully, I've convinced you that both omitted variable bias and reverse causality are unlikely to be major threats to the estimates that we found. Okay, so now we're going to move to a panel context, which is that we're going to disaggregate basically GDP at the country level, but we're still going to study the impact of global temperature on GDP. Okay, so we're going to get GDP data for most countries in the world from standard source, dependent world tables, and then for some countries we'll be able to go back all the way to 1900 using the macro history database. Okay, so that's going to be a different set of countries, just 18 currently high-income countries. Temperature data is completely standard and coming from standard sources. And the final thing that we merge into that database is extreme weather information. So how do we get that? Well, from Izimit, we get daily measures of precipitation, temperature, and wind speed for every latitude, longitude, cell, and day in the world, starting in 1900. And then from that, we are going to aggregate those measures into measures of extremes at the country level. So we're going to count the number of cell day pairs that are above a certain threshold within a given country. And then the fraction of those cell day pairs that is above the threshold is going to be our extreme event indicator. Okay, so with this data set in hand, we can do many things. The first thing we do is to simply replicate our time series analysis now in this panel context. So we're still going to look at the global temperature shock on the right-hand side, but we're going to disaggregate GDP at the country level on the left-hand side, so that we can be a little more flexible in terms of controls, country fixed effects, and country level controls as well. Reassuringly, but also not surprisingly, we found a very similar estimate in this panel specification as we've found in the pure aggregate time series specification. The dashed red line is our initial set of our initial estimate, and then the black line is the average effect that we get in the panel. Okay, so now that we've just shown that the basic estimates are the same, we're going to use this panel specification to do a lot more exercise. Okay, so the next exercise that we do in the panel is to think about external validity. So the first thing we check is whether our estimate is stable over time or whether it varies a lot. And what we show in the left panel here, in panel A, is that actually this estimate is remarkably stable over time. So the black line is the baseline. The dashed red line is if we start the sample after the oil shocks of the 70s, so starting in 1985. The yellow line is if we start all the way in 1900 using the macro history database. And then we also stop before the financial crisis. That's the dotted purple line. And you can see that all of these lines basically lie on top of each other. If anything, the one starting in 1960 is the smaller of all of them. And so that's telling us that the estimate is pretty stable over time. It's also telling us that there doesn't seem to be a ton of adaptation to these global temperature shocks, because given that temperature is slowly trending up in the background, the level, if there was a lot of adaptation to these temperature shocks, we should see the estimate gradually weaken over time, and that's not really what we see at all. Panel B then shows you that our estimate is actually doesn't rely too much on the type of temperature variation, the fundamental cause that's moving around global mean temperature, but it really seems to be coming from the effect of temperature on GDP, regardless of how global temperature is formed. And so we show that by explicitly controlling for an El Nino index and controlling for volcanic eruption. So basically what you're left with is variation coming from solar cycles. And you can see that, again, all these estimates are extremely similar, which is, again, telling us that this estimate is stable across types of temperature variation. And finally, you may be worried that, well, maybe if there was no omitted variable bias at the global level, maybe there is at the regional level. And so we can also address that in this disaggregated specification. What we do in panel A here is we saturate the specification with country level control, so 10 lags of world GDP and country level GDP. We include region specific trends that are going to absorb potentially confounding shocks, say for the Southeast Pacific. And again, you see that our estimates are remarkably stable across these specifications. And finally, panel B just shows you the pre-trends that I hadn't shown you so far. They're mechanically 0 in years -2 and -3 because we have 2 lags of GDP, but we can go all the way to -6. And you can see here that our results don't seem to be driven by a differential pre-trends. Okay, so hopefully so far I've convinced you that the causal effect of global temperature shocks on world GDP is actually substantial and fairly stable across specifications. And so what we can do now is actually compare this impact of global temperature to the more conventional estimate of the impact of local temperature on GDP. And so we've set up our data set and our empirical specification so that we can make this comparison as cleanly as possible. And so what we can do now is take the same specification as I've been showing you so far in disaggregated at the country level, and we can simply replace the global temperature shock with a local temperature shock that's constructed in exactly the same way. Okay, so we're basically just have an I subscript, a country subscript in this specification, and that's the only difference. Now, of course, when you're in a panel, you're tempted to throw in a time fixed effect because that's the more conventional specification. So we're also going to do that. Of course, we could not do that in the case with global temperature. All right, so these are the results that we find. So the 2 red lines are the impact of local temperature on GDP. So in both cases, with and without time fixed effect, the initial impact is about 0.5%, and then it gradually increases to about -1.5%, and then mean reverts a little bit. You can also see that including or not including the time fixed effect doesn't make much of a difference, and that's coming from the fact that the global controls we included, already in the time series case and in this case, they actually do a good job at capturing the world economic cycle. So that's also reassuring for the global temperature specification. But the main message that you get from this picture is not whether the time fixed effect matters or not, is actually that global temperature affects GDP much more than local temperature. At peak here, it's about 6 to 7 times more under global temperature relative to local. Okay, so I should say, if there's one graph that you want to remember from this talk, this would probably be the one graph to keep in mind. Of course, it begs the question, why is it the case that global temperature is so much more detrimental to GDP than a local temperature? And so we started with an intuitive explanation for economists, which was economic spillover. Now we thought that because countries are linked together, and we tend to trade with countries that are close by, and local temperature is shocks or spatially correlated. In that case, the local temperature specification would actually be misspecified. We're missing a spillover component that captures these economic linkages. And so we started out with this idea in mind, and we tried to test it. How did we try to test it? We constructed external temperature. What do we call external temperature? It's a weighted average of the local temperature shocks of all of the trading partners of any given country, and the weights are the trade fairs. Okay, so that's the type of variable that would come out of a standard trade model, and you would want to include that in the regression. And so there are a couple of recent papers that make that point in different contexts. Now, when we do that, what do we find? Well, when we horse race this external temperature against global temperature in panel A here, we actually find that external temperature doesn't matter at all. Okay, so it's basically a 0. If you look at it in isolation, it will have a small effect, but it gets completely swamped once you include global temperature in the analysis. Here, the shape is a little different because we don't have trade for all countries, so the set of countries is just slightly different here. Okay, so that's telling us here simply that economic spillovers, at least through trade, are just not strong enough to rationalize the large gap between local temperature and global temperature. And that actually makes intuitive sense, because on average, the world, and the average country in the world is not that open to trade, maybe 20% on average. And so if the baseline impact of local temperature is moderate and the world is not that open to trade, we wouldn't expect trade linkages to actually lead to a massive amplification of the effect of local temperature on economic activity. Okay, so having discarded that explanation, we turn to a second hypothesis, which was that, well, perhaps global temperature is simply a fundamentally different object than local temperature. And what we conjecture here is that global temperature is simply a better summary statistic of the state of the climatic system than idiosyncratic local temperature realizations. And that in part makes sense, because global mean temperature includes ocean surface temperature, and the temperature of the oceans is a key driver of evaporation patterns, wind formation, hurricane formation, as we've sadly seen in the US in recent days. And so it could lead to, it could be that global mean temperature changes actually, captures in a more comprehensive way, all the changes in the climatic system relative to local temperature. And so this is where we can use our extreme events data. So what we do here is to look at whether we can predict extreme events with our global temperature changes, and then compare that to the predictive power of local temperature change. So there are a lot of figures here. Let me walk you through them. So panel A shows you how extreme heat, which is, again, a large fraction of cell days in any given country above a temperature threshold, respond to global temperature changes. That's the solid black line with the blue standard errors. And you can see that it's quite substantial. After a global temperature increase of 1 degree Celsius, you see that the frequency of extreme heat increases by about 5 to 10 percentage points on average. Now, this index has a baseline probability of 5%. So this means that after a 1C global temperature change, extreme heat doubles in frequency at the country level. So that's a substantial increase. The red line shows you the same exercise when we put local temperature on the right-hand side. And you can see that, of course, if local temperature goes up, there is an increase in the frequency of extreme heat, because that does shift the temperature distribution, but it's much less pronounced than when there is a global temperature increase of the same magnitude. Okay, so the global temperature seems to be capturing the extremes, the tails of this temperature distribution better than the annual average. And then we repeat the same exercise for droughts, so low precipitation cases, extremely high precipitation cases in panel C, and extreme wind, high wind speed, surface wind speed realizations. And you can see that, of course, the responses are not always super precisely estimated and can be a little jaggy. But what you can see throughout, the main message is that the frequency of those extremes is actually always much more responsive to global temperature increases than they are to local temperature increases. Okay, so qualitatively, it seems that these extreme events, could be a plausible rationale for the larger effect of global temperature relative to local temperature. And then the question is that the case quantitatively? And so that's what we show in the panel on the right. So here, there's a number of steps that go in this figure. And so let me walk you through that. So what we do then is, okay, we've estimated how the frequency of extremes responds to global temperature and local temperature. Then we separately estimate the impact of these extremes on GDP. So that's a standard panel regression, like the local temperature regression. And then we interact these coefficients, how the frequency, construct a shift chair, if you like, predictor, where we interact how the frequency responds to global temperature with the damages associated with any given extreme. Then we add all of them up together with local temperature, and then we get the dashed red line in this figure. And so you can see that we can actually get quite close to the impact of global temperature that we've directly estimated in black. So when we aggregate the effect of all of these extreme events, we get about 2/3 of the main estimate. So that's telling us two things. First, that the differential predictive power of global versus local temperature for extremes is actually a plausible explanation for the large gap in their economic effects. But second, it's also telling us that doing this aggregation exercise is not easy. These data sets used to construct extreme events are massive, and so they're not, and then you have to specify exactly what type of extremes you want to throw in at this analysis. You have to say, oh, I need to look at extreme heat defined as the 95th percentile of the temperature distribution. Extreme wind, extreme precipitation, so you have to specify thresholds, and perhaps these thresholds are not the ones that or correspond to the true model of the world. Here we had to make a lot of choices here, and we could only get 2/3. And so from a practical perspective, it's much easier to directly estimate the impact of global temperature on economic activity. All right. So hopefully by now I've convinced you that global temperature has a large effect on economic activity, and they seem to be mostly driven by extreme events. And so what I want to do one thing I wanted to show you before we move to the model is that these effects are not confined to GDP or GDP per capita. You can also see them in investment, the capital stock, total factor productivity as estimated in the Penrose tables, as well as labor productivity. And these effects are also not uniform across regions of the world, but they're actually much more uniform than the effects of local temperature. So what we find is that in North America, once we disaggregate the effects by region of the world, our effects are actually pretty similar to the world average. But in Southeast Asia, they actually peak all the way at 20%, which is almost twice the global average. And in Europe, they're somewhat milder than the global average. But across most of the regions of the world, actually, the effects are negative, which is quite different from the local temperature results, where some countries gain and others lose. Here, almost everybody loses from global temperature. Okay, so with these results in mind, we're now going to move to a very simple model of the world economy, and that we're going to discipline with these reduced form estimates. It's a very standard model because it is the neoclassical growth model. And so households in this environment maximize the discounted stream of utility of consumption going forward, subject to a standard budget constraint. They earn labor income and interest income, and then firms who rent labor and capital from households, maximize profits subject to a Cobb-Douglas production function. And the only way climate change enters this economy here is through these damage functions. So temperature affects productivity and it affects capital appreciation. How are those effects specified? Well, we're going to specify damage functions that allow for delayed effects, and that's going to be important to capture this internal persistence of temperature in response to a temperature shock that I was talking about earlier. And so we're going to say that a temperature shock as periods in the past has affects productivity today according to zeta S. And so zeta S, this whole path is the damage function for productivity, and then we have a similar damage function for capital depreciation, little delta S. The name of the game now is to estimate these damage functions, and so we're going to do so by matching exactly the output and capital depreciation responses in the data. How do we do that? Well, we leverage the fact that the historical temperature shocks that we exploit are relatively small. Remember, they were 0.1 C, and so we're going to log linearize the model. That's very easy to do, and then we get a very simple mapping between the observed GDP per capita response and the observed capital response that I've shown you in the data. Get difference them out, and then we're going to recover a productivity sequence that corresponds to a 1 degree Celsius global temperature change. That mapping is very simple for productivity. It's a little more complex for capital because it reflects the forward-looking decisions in the model, but we can still invert it after log linearizing the model, and then we're going to get a sequence of z's and a sequence of deltas. That's still not the damage functions. Then, taking into account the internal persistence of temperature, we're going to basically get the structural damage functions as innovations to productivity and capital depreciation. Okay, so that's how we do it. And of course, there's more details in the paper. Once we do that and we target the global temperature impulse response functions that I've kept showing you so far in the talk, we find that at peak productivity declines by 3%. So that's much smaller, of course, than the 12% that we found because of for GDP, because of two reasons. First, we're netting out the capital response, and second, we're accounting for this internal persistence, which actually, drove a lot of the peak effects 6 years out. By contrast, productivity declines only by 3%, and that peak happens much earlier, about 2 or 3 years out, because again, we've corrected for the internal persistence of temperature. Okay. Now, when we repeat the same analysis with local temperature instead, we find much smaller numbers for both productivity and capital depreciation, which is simply reflective of the fact that the empirical target was much smaller. We get a 0.5% productivity impact at peak and a smaller capital depreciation effect as well. And now we're in a position to construct the counterfactuals that we're interested in. So for a climate change scenario, it's very simple. We simply specify a path of global mean temperature relative to a baseline, say today. And so in the exercise I'll show you next, we're going to start to take time zero as today, start in steady state, and then feed in a warming scenario that gradually adds 2 degrees Celsius relative to today. And so we're going to be in a 3-degree world by the end of the century relative to pre-industrial levels, because we've warmed about 1 degree so far. And then to construct the social cost of carbon, what we do is we feed in the temperature path that corresponds to a one-time pulse of CO2 that's released in the atmosphere. Okay, and then the social cost of carbon is simply the equivalent variation that makes household indifferent between steady state and the world with the CO2 pulse as a stock valuation. And then when I'll show you welfare numbers, I'll use the more conventional flow, percent of consumption that you would have to forego every year in order to be indifferent. Okay, so these are our main counterfactuals. So panel A shows you the path of temperature that we feed in. So starting at 0 in 2024, gradually increase, reaches 2 degrees C by the end of the century, and then tapers off. Panel B shows you the path of output that's associated with this path of temperature. The dashed red line here shows you the path of output when you use the structural damage functions that you estimate using the local temperature number. Okay, so that would be the conventional counterfactual, if you like. And you can see that climate change does affect world output, and by the end of the century, output has declined by about 7%. Okay, so that's actually in line with a lot of the numbers out there. So it's not nothing, but it's also not dramatic if you think that there's going to be economic growth regardless of climate change. Now, if you target use the structural damage functions that you get from targeting the global temperature estimates, you get something much larger. Output declines much faster and reaches almost minus 50% by the end of the century. So that's about about a 5 to 6 times increase. The path of capital, largely tracks the path of output, and so does the path of consumption, which again is down 7% by the end of the century under local temperature, but is down nearly 50% by the end of the century under global temperature. And then welfare is the appropriately discounted valuation of these consumption paths. And so under local temperature, the welfare impact is 4%. And so, again, not nothing, but also doesn't seem too dramatic. However, under global temperature, the welfare impact of climate change is much more substantial and reaches 29% in consumption equivalent percent, already today. And then, of course, these effects gradually worsen to converge basically to the consumption drop once you reach the new steady state. And of course, the welfare jumps because households are taking into account the full future path of consumption under climate change. And then finally, you can use the model to construct the social cost of carbon, and you can see that under local temperature, you have something that's in line with conventional values, around $200 per ton. Whereas under global temperature, you get something much more pronounced in excess of $1,000 per ton. So these are all large numbers under global temperature. And so one natural question is, well, why didn't we notice those effects before? Surely, we should have seen something in GDP. And of course, we do see something in GDP because that's exactly what our empirical exercise, captures. But the observation that we make here is that, these temperature shocks, once you take out the trend, which you can never distinguish from anything, these global temperature shocks, historically, they're not that big. They were, about 0.1 degrees C. And so the GDP fluctuations that they imply were about 1% at the world level. And a 1% change in GDP year to year is actually swamped by background economic variability. So that's what we show in panel A here, where we show, we repeat our counterfactuals, but feeding in the historical path of global temperature. And the blue line is, basically the data with climate change. And then we use our model to construct the counterfactual path of world GDP absent climate change. That's the dashed red line. And you can see that, throughout the second half of the 20th century, you can't really distinguish the impact of climate change on GDP year to year. You would actually have to run the local projection that we have to actually, tease out those effects from background economic variability. But you do see an effect, year to year, and the key here is that these effects are persistent. They don't go away. Every year, world economic growth is reduced by climate change. In the 21st century, actually, because warming has substantially accelerated, we find that about 1/3 of world economic growth is actually lost to climate change, which incidentally could give you yet another explanation for the slowdown in productivity. Panel C then shows you what that applies for the level of GDP, and what we find is that world GDP today would be 17% higher if we had not had historical warming since the 60s. And in fact, we also find that these effects are not done materializing, even if temperature stopped, because there are delayed effects in the damage functions and in the model. And so actually, 8 percentage points of those losses are still to materialize. The last thing I'd like to show you before I conclude is sensitivity with respect to key parameters. Of course, there are a number of choices and the parameters that we've picked that matter for counterfactuals. Now, remember, we're always estimating the structural damage function. So those are always internally estimated, but depending on the rate of time preference of households, you could get different implications for welfare and the cost of carbon. So the first column shows you how the welfare numbers and the cost of carbon are sensitive to the rate of time preference. So our baseline is a rate of time preference of 2%. If you think that households are actually more patient, of course, the welfare numbers become smaller because most of the losses happen in the future. But you can see that under global temperature, the impacts are still, substantial and excess of 20% for most of the plausible range of the rate of time preference. And the relative, global versus local is of course very stable. That's always a factor of 6. The discount rate just moves around the overall level of damages. The social cost of carbon, because it's a stock valuation, is also fairly sensitive to the rate of time preference. And you can see that, of course, it becomes a bit lower if households are more patient, but it's still in excess of $500 per ton. And if you think that households are actually very patient, like some have advocated, that the social cost of carbon can exceed $3,000 per ton. Of course, if you think that we're going to warm more than 2 degrees C by the end of the century, that's panel C, then the welfare losses are going to be larger. And then the last point I'd like to emphasize is the climate sensitivity. So we've actually been fairly conservative in our climate sensitivity. We've used half of the median in Dietz et al. Why? Because it makes the historical emissions and historical warming a bit more consistent. But if you use the median climate sensitivity instead, the one coming from leading climate models, actually you get a social cost of carbon that's much closer to $1,700 per ton under global temperature. All right. So hopefully, now that we're nearing the end of the talk, I've convinced you that climate change has substantial possible effects on world economic activity, historically, and also going forward in time. And so what I'd like to do in the conclusion of this talk is to simply delineate the implications of these numbers for decarbonization policy. Okay, so now this is outside the model. This is just rule of thumb type numbers coming from the conclusions from our paper. So in the Inflation Reduction Act, most decarbonization policies cost about $80 per ton. That is below conventional social costs of carbon value. So let's take our own number, $200 per ton under local temperature. So if all the countries in the world said, "Oh, let's cooperate and let's decarbonize all together," as if we were just one world government, then we should all engage in widespread decarbonization right away because the cost is 80, but the benefit is 200. However, if you think that to some extent governments act non-cooperatively, unilaterally in their own self-interest, then they're going to care only about losses that happen within their borders, not across the world. And in that case, the social cost of carbon is not the right object to look at. You have to look at the domestic cost of carbon, which, say, for the US is much lower than the social cost of carbon. It's only $45 per ton because the US is about a fifth of world economic activity. And so in that case, unilateral non-cooperative decarbonization policy is not cost-effective. What our estimates do is that they actually flip this trade-off. Under global temperature, even the US only domestic cost of carbon is around $200 per ton. And so that's much larger than the cost of decarbonization. And so we should, to the extent that, if you adopt these numbers, you should actually engage in more decarbonization policy because now it's cost effective from a purely unilateral perspective. And so I'll leave it at that. And thank you very much for your attention. And I'm excited to hear your questions.
Great. Thanks so much, Adrien. So while we gather some questions, maybe I'll start us off. So first, I think that the huge innovation of this paper is looking at global temperature relative to local temperature impacts. So do you want to expand a little bit more on this methodological advance and maybe how you relate to previous work like the Jones, Dell-Olkin paper? And then second question, just related to something that's been asked in the chat by Agnese Kadali. So on the mechanism being extreme weather events, do you get the sense that this is being driven by, say, developing countries coming up into the aggregate results? So my sense would be maybe the US is not really that affected by extreme hurricanes, even if you get a couple a year, but maybe places like India, Pakistan would really be. And then, so go for that, and then I'll collect more questions.
Great. All right, two great questions. So yes, so on the methodological aspect of the paper, I mean, in some ways we're in terms of, so we do things differently than than the literature has done, but the data was there, time series methods were there. We just used an old method on old data and came up with new numbers because doing that exercise is the core of our paper. So the Dell et al. I think is the Dell Olkin Jones is, as you said, is the first paper to estimate in a systematic way in a panel setting the impacts of local temperature on economic activity. So actually, maybe a more useful object to look at, slide to look at is this one. So basically, the empirical specification in the Dell Olkin Jones paper is this one that we've run exactly for local temperature. So there we're just replicating their approach with our data. We also did it with their data, and again, you always find consistent numbers where you project world GDP, country level GDP, H periods into the future on a temperature shock at time t. And the key here is that in the Dell et al. Paper, the temperature shock is local temperature. Okay, so it's the average within the country of temperature in a given year. And so the only thing we've done really here was to replace this local temperature shock with global temperature shock. And of course, when we started, we didn't even know whether there was going to be enough variation in global temperature to estimate effects plausibly. And to some extent, we were a little bit surprised to see that because of all this natural climate variability that there is around the trend, we were actually able to estimate something that turned out to be very robust across specification. So I would say that's really the innovation here. On the question about extremes and developing countries, that's a great question, and it does relate to the to this figure, the one I briefly flashed over, which is the effects of global temperature by region on GDP by region of the world. And you might think that the US is indeed a little bit less affected by extreme events than, say, India, and perhaps the mix of these particular extreme events, maybe it's more hurricanes in the US and more extreme heat in South Asia. But actually, you can see, and we were somewhat surprised by these results, but you can see that these effects are actually fairly consistent across regions of the world. It's hard to go at the country level because then you start losing statistical power for small countries at least. But for these large regions of the world, we can estimate those impact region by region. And in in North America, the effect is maybe a little bit less than the world average. It's like peaks at 10%, and maybe mean reverts also a little bit faster. For South Asia, it is peaks at 10% too. It's really Sub-Saharan Africa and Southeast Asia that are the two regions that are most exposed. So what you could do in principle, what we haven't done, is to try to then estimate the effects of extremes region by region and try to see whether a given high precipitation event is more damaging in South Asia than it is in North America. That would be something very interesting to do that we haven't done. But certainly it seems that the effects are relatively detrimental. And yes, perhaps we're a bit more adapted to say hurricanes in the US, but property values are also high. Reconstruction costs are higher than in India. And so in dollar terms, it's not clear that the damages are necessarily that much lower.
Great. So now I'll call on Yasmin. She's got her hand raised. Yasmin, go ahead and unmute yourself.
Yes, so it's a super interesting paper and a lot of work that you've been doing already here. So probably you have an appendix slide to actually give an answer to my question. But what I was actually wondering is whether the results so far take into account that agents may re-optimize in response to a changing environment. So if we see, for example, extreme weather events intensifying, you would expect, right, that economies may try to harness themselves against those potential impacts so that adaptive responses, but perhaps also our efforts to mitigate climate change may become stronger over time if there is some effect of learning there. So I was wondering whether you take some response that agents have here as given, or whether there are some adjustments occurring in response to a more intensified climate change.
Yeah. No, it's a very important point. And with this empirical strategy, we are a little limited in what we can say about adaptation. So I think the one result that we have that speaks most closely to that is this panel A here, where we've estimated these effects across time periods. And remember, global temperature is going up in the background. And so if we're continuously adapting to a worsening weather, then you would expect the damage, starting in 1900 to give you a very large number, then starting in 60 to a smaller number, and then starting in 1985 to a even smaller number. But we're not really seeing that. So that suggests, it's not conclusive, but it suggests, I would say, that historically, at least, there's not been a lot of adaptation to these extreme events. Now, what you could say, and I think that's what you hinted at, is that, well, maybe people didn't really realize that the frequency of these extremes was going up, and going forward, there's going to be more adaptation to the impacts of these extremes, and that's certainly possible. And you might hope so that we eventually adapt to these extremes. That's not but hypothetical adaptation in the future is not something we can inform with data, and so that's why we're kind of limited to this historical analysis. The other thing that, so even if you're very optimistic about adaptation going forward, our numbers would still give you the willingness to pay of society for these adaptation investment, which are sometimes very expensive. They don't come up for free, and so even in that world, what you can say is, well, if I'm going to fully adapt to hurricanes and it costs me X dollars, then what is the benefit? It's some fraction of this 12% number, and then you can compare cost and benefit.
Yeah, that's really interesting. Thank you so much.
Great. Now in the Q&A from Daniel Hardy, we've got a question. Are your estimates conservative because you cannot capture non-linear effects of changes larger than seen historically, or maybe chronic effects such as permanent drought?
Yes, again, so it's a great question because it connects. It's exactly the flip side of the one that Yasmin just asked. It's because it's adaptation would give. So basically, it all comes down to, we're using a log linear specification, and then we see shocks that are that big, and then we scale them up to this. If you have adaptation, you would expect this relationship to become concave with the size of the warming, and nonlinearities would give you a convex relationship, tipping points. And of course, because the shocks that we observe are fairly small, there's not much we can credibly say about either concavity or convexity. I'll again fall back on this exercise where we've re-estimated the impacts across time periods, and because temperature is gradually rising in the background, that's a little bit like estimating an interaction effect. And so what this is telling us is that we can detect a lot of convexity in damages. So we can detect a lot of nonlinearities or a lot of, concavity. So really, the full answer to this question and to Yasmin's question is that either there is neither adaptation nor nonlinearities in the sense of convex damages, and so everything looks fairly linear, or there's both, and they kind of always offset each other to the point that the damages of these temperature shocks are kind of the same across time periods and across baseline temperature of the world. So these are all super important questions when we start thinking about these large counterfactuals. And so here kind of we do the best we can with these temperature shocks that are the only ones that we can credibly use for identification at the in this time series context. But you can imagine doing a lot more on adaptation coming from disaggregated settings where you then aggregate micro level adaptation responses to the country or world level. And I have some other work on that, and I'm sure many people in this talk are also working on these adaptation topics.
Wonderful. So we might take one more. This one's from Francesco Paolo Mongeli. He says, I'm a bit puzzled by the Europe chart. We know that Europe is warming faster than other continents. Could global temperatures underrepresent the higher European warming?
That's an important point. So yes, Europe is warming a little bit faster than the world average. This is all conditional on temperature, global temperature. So if you think, well, a global temperature increase means more local temperature changes in Europe, then that's where the question comes in. It says, well, we should see larger effects in Europe. So that's true, but remember, local temperature was a pretty small effect, had this pretty small effect to begin with. And in fact, if you look at heterogeneity in the effects of local temperature by region or by country, that's the famous Berg-Xiang-Miguel paper. Actually, Europe sits at a point where it's the effect of local temperature is pretty close to zero, because there's a mix of hot and cold countries in Europe, and so as a continent, the economy of Europe is just not very sensitive to local temperature. So even though yes, it's warming faster, and so if you live in Spain or Italy, actually you very much feel the effects of this higher local temperature. If you live in Sweden, actually you may like the higher temperatures. And so what we find is actually a result that global temperature is actually still substantially more damaging for Europe's economy than local temperature. It peaks at here 7%, whereas the conventional result for local temperature for Europe is closer to a zero effect. So that could be that acute heat waves that are better predicted by global temperature in places like Spain or Italy are actually more than offset the gains in places like Norway or Sweden, or it could be that we're also picking up heavy rainfall here, which we've seen in the news recently also can affect Europe's economy.
Great. Well, that's about all we've got time for. So thank you so much, Adrien, for that fascinating presentation. I should say thank you to Diego too, who's your co-author and who's also here on the chat. Thanks to the audience too for such great discussion. Our next webinar will be taking place on October 14th, when we have Maxime Suzette from Boston University talking about his research on green intermediary asset pricing. I'm going to put the link to that in the chat window, so please register for that. And if you've got a paper to submit for consideration, please send it along to info@eaxes.org. Well, thanks again, Adrien, and it was really a pleasure talking to you.
Thank you very much, Connor. And then again, thanks everyone for your questions and your attention.
Thank you, Adrien.